Good evening, ma'am.
Mm. Mhm. Good evening. Am I audible? Uh, am I audible?
Yes, ma'am.
So I think we should start. Yeah, so good evening, everyone. Uh, I'm Liza, one of the assigned TAs to this course, Microprocessors and Microcontrollers, and I'll be taking your interactive session this this week. And we'll be taking up some questions from week 3. And before solving some or getting some problems done, we'll be revising some of the this week's lectures, past week's lectures, right? So, starting with the summary. So, for and the foremost lectures deal with these topics, and we'll start with branch operations. So, what are branch operations? Branch, as you can see, is different from the main program, right? So, any instruction that makes the MUP to execute some of the instructions which are not in main program are called branch operations, right? Or branch instructions. So there can be two kinds of branch operations, unconditional branch or conditional branch. Unconditional branch in which you just tell the MUP at some point of your main program that do this, break the loop or something like that. And conditional branches, which is dependent on the execution of that branch, is dependent on the execution of or the result of the operation of the previous instruction, right? So yeah, these are the branch operations. Then we had jump conditions and counter. We'll be practicing some of the questions regarding this. So basically, when you want to get some delay or you want to execute some instruction or some program like uh, more than once, like multiple times, so you use loops, and in the loops you need counters because you need to control how many times that loop will be executed. So in the execution of the counter we need jump conditions, so that once it first iteration is done, it goes back to the starting of the program that has to be repeated in the loop, right? So jump conditions are important there. Then we have register pair as counter. So there can be cases when your normal 8 bytes cannot suffice the times of the times in number of times that you want to execute some operation, right? So in that case, you need to increase your count. So to increase your count, you can use register pair, which has you can as has double the bits, 16 bits, uh, and since the number of counts is increased, you can execute your program or instruction more times than the 8 bit count, right? Yeah, so Uh, timing diagram has basically two parts, uh, fetch cycle and execute cycle. In fetch cycle, you fetch the MUP fetches the opcode, and in the execute cycle, either memory read, memory write, IO write, whatever is the instruction in the whatever the operation that is to be performed in that instruction that is coded in opcode, that will be performed, right? So basically, yes. Uh, You have a question?
Yeah, actually, I have confusion regarding this timing diagram. So, will you
Yes.
please elaborately tell this?
Okay, yeah, sure. Anyways, we were going to discuss some questions. So, eh, let me explain first, and then you can ask where the doubt is, or if it's not clear, then also. Okay. So,
Yeah, sure.
basically, any instruction has two parts, opcode fetch and the execution part, whatever the opcode is about, whether you want to write in memory, read from memory, IO read or IO write, right? So, any instruction cycle, let me write instruction cycle has two parts, fetch cycle and execution cycle. Right. So in fetch cycle is typically just the opcode is fetched from the memory. The MUP is fetching the opcode that is written in program, and that is the fetch cycle. And then after that opcode is decoded, then the MUP gets to know what is to be done, and the execution takes place. Okay, this is the basic idea of a instruction cycle. So uh, I can divide. So if let's say you have seen the timing diagram, right? So you know that if this is the clock, this is the first time cycle or first T state, whatever you like to call it. Fourth, fifth, sixth, seventh, right? So first T state starts from here, ends here. Second starts from there and ends there, and this is where seventh one ends. Okay, so let's say you have an instruction. Let's start by an example, or take a journal instruction cycle. What will happen in an instruction cycle? You'll have an opcode, and then you'll have some operand, right? So what will happen in first four T states? Uh, first four T states are called first machine cycle. Machine cycle, and these next will be called in a typical a journal instruction cycle. Okay, this is the second machine cycle. Okay, and this whole makes up one instruction cycle. Okay, and as you already know that this first machine cycle is for what? Can someone write in the chat? What would be the
Opcode,
first
opcode fetch.
good fetch, right? So this first machine cycle is actually opcode fetch. And then what is this spelling? Depending on what is the opcode, whether it requires operand or not, or generally for all the instructions which require operand, this second machine cycle will take place, and after the second machine cycle has taken place, one instruction cycle will be complete. Okay, just in case, like an is the okay, leave it. So first is opcode fetch. The second is this is the execution cycle. Right. So Opcode fetch is the compulsory machine cycle. It will happen and it will happen first and foremost for any instruction. Okay, that much is clear. Then what else? Generally, opcode is of 4 T states, but it can be 6 T states also. The examples I'll give later, like maybe you'll know already call instruction or DCX, INX instruction. These take the opcode cycles of 60 states. Okay. But generally it is 40 states only. Then what else? Yes. So you know how instruction cycle is actually how is what is it composed of? Two machine cycles, and all of these machine cycles contain T states, right? From the clock. Next. So what will happen during first T state? If let's take an example only. This is first, second, third, fourth, right? So first T state starts from here. And so what will happen in first T state? We know these four are for upward phase, right?
Yeah.
Yeah. So in first T state, what all will happen is let's say during T1, what will happen? Higher order address will be loaded to the higher order address bit will loaded onto the higher order address lines. So one thing that will happen is A15 to A8 will get the higher bit byte of address, right? What will happen other than that? During this first T1, your ALE is high because ALE is high because at the starting of any instruction you need to get the complete address, which means if ALE is high, then AD7 to AD0 will have lower order address,
Yes.
right? What else? What other signals do we have? Read, write, IO. Yeah. So read and write, read will be okay. This is the question. What will be the read signal at starting of um, at T1 during T1? For the timing, let me admit some people. Yes. Simple logic. What are we doing in the first T state? Getting the data or getting the address. Where are we getting it from? I mean, MUPI is reading the address, right? From the instruction, right? So what should be the read signal? Read is enable low.
Yes.
Read is enable low. So MUPI will only read if this read signal is low, right?
Yes.
Which means if MUPI has to read the address, this read signal has to be low, which means has to be low. I'm doing it. No, actually, read goes low during the op. Yes, sorry. Read is initially high during T1. Yeah. So read write are read and write, since there is no operation is being performed, the signals will be high. That doesn't really matter because MUPI is not going to operate on anything. It just fetches the address. Gets latched onto it. So yeah, our low. What else? IO memory. Oh, IO memory signal will be, since the address is in the instruction and instruction is in memory, so MUPI has to read it from the memory, which means for getting the memory, this memory should be enabled, which is actually enable low. So this signal should be 0 so that the address can be fetched, right?
Yeah.
Is it understood? So this is during T1. During T2, during T2, now since we have already gotten the lower order address, ALE will have to go low so that the data can be fetched, right? Data here will be opcode. This is the fetch cycle, remember? So ALE will go will go low so that data, which in the fetch cycle is actually opcode, can be loaded onto AD7 to AD0. Okay. So during T2, ALE goes low. What else happens? Since now data has to be read, I was jumping ahead of myself. So during T2, our read signal goes low because opcode has to be read from memory. So this read operation has to be done. That is where read will go low. And since there is no writing being done, write will be as it is. What else? Yes, this happens during T2. And during T3, your data will remain on this lower order address bus only, lower order data address bus. Data remains on AD7 to AD0. And this time is used since now we have fetched the opcode is decoded. See, it's like a sequence. First, you get the address from where the instruction you are going to get or the opcode you're going to get. Then you get the opcode and then you actually decode the opcode, right? And yes, you have a question? Okay. Uh, yes. So during T3 and T4, actually, this time is used to get this opcode from the database to the MUPIC, and during T4 only it's decoded, right? So, since sirs also told this that T4 is kind of that dash thing, right? So basically, during T3 and T4, you have already the opcode is there from you have the MUPI has fetched the opcode. This time is used to get that opcode from databus to the MUPI itself, and then in T4 it's decoded, right?
Yeah.
Uh, yes. What else? So this is opcode cycle fetch, opcode fetch cycle. Is it understood? Or if you have any other question apart from this, then you can ask whatever the confusion was.
No, it's okay.
So this was the opcode fetch cycle. After this, whatever is the operation that needs to be done will be happening during these cycles. 5, 6, 7, memory write, memory read. All the examples were covered by Sir. And yes, should I do memory read cycle also? I think I can take an example in my
Yes, ma'am.
screen. Okay. Memory read, memory write for both.
Both, ma'am.
Okay. So I'll take the same example as Sir did in class, if that's okay.
Yeah, that will be better.
Okay. So let's take this example. Mm-hmm. So from picture, yeah. So the code is MVI A 45H, and since you know this is a 2-byte instruction, and the corresponding code for MVI is, you know the meaning of corresponding code. When I say the corresponding code for
3E
MVI,
it is.
yeah,
MVIA, I think.
three. No, I'm not asking if you remember it. I just want to know if it's clear why I'm writing a
Yeah,
number
yeah,
for
yeah.
MVI. Yeah,
Hmm.
3E, right? So, which means, and if this is placed at some 2000 address location, right? So, what will be the actual structure of the program? At 2000, you will be having this MVI code, which is 3E, and at 2001, you'll have this 45. And remember that both of these are hex numbers, right? This much is clear. I think next part will be
Yes, yes.
fine. Okay. So let's say if this is our clock, mm, 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 right? This is the clock. It will be A15 to A8, ALE, read. Uh, okay. Let's make right here and I here. So this is clock. This one is A15 to A8, AD7 to AD0, ALA, uh, read, write. Alright, I am. Okay. First, second, third, fourth, fifth, sixth, seventh. And okay, so as we discussed just now, what will happen in first cycle will so let's differentiate between this is opcode fetch cycle and this is the execution cycle 567. So A15 to A8 is just used for the higher order memory only. So during the whole opcode fetch cycle, these the during the whole instruction cycle, A15 to A8 will contain the higher order address. They will not be disturbed once the address is loaded. Okay, is it clear?
Yes, ma'am.
Huh. So during first T state until it is the instruction cycle is complete, the A15 to A8 will contain the address, higher order address. And what is the higher orders here?
Excuse me. So the instruction cycle is the entire 7 T states, right? This is the first machine cycle of that instruction cycle.
Yes, sorry, yeah. Fetch cycle, for the entire fetch cycle.
Yeah,
Yeah, so what will be the higher order address here?
20.
20, right? So A15 to A8 will contain 20 here. Now, after, let me, hmm. So, what will AD7 to AD0 contain during the first T state?
00.
00 because that is the lower order address, and first of all and first and foremost, the any instruction needs complete address, and that is why AD0 will AD7 to AD0 will have the lower order address. And how will that be loaded onto the data this address come data bus? By using this ALE signal. ALE signal has to go high so that this lower order address can be loaded onto the bus. So, and we know that this happens only for first T state because after that data has to be loaded, right? So during this first T state, AD7 to AD0 will have 00H, that is lower order address, and ALE signal will be high during this state. After that, ALE signal will have to go down so that the data can be loaded. So after first T state, ALE signal goes down and remains there for the whole time because we don't want to lose our data. Once we get the address, we don't want, once we get the address, lower order address on the latch, we don't require it, the lines for any other purpose other than holding the data, right? So ALE signal will remain low, and as okay, these are read. And read will stay high for this because there's no reading done here. Next, what will happen? Since has gone low, we need to retrieve the data. And data in fetch cycle is actually opcode. So for reading the data, the opcode with, I mean, this program is written in memory, right? So UP has to read it from the memory, which means read signal has to go low. It has to go low to read the opcode from the memory. And since it's a memory operation, this memory signal will be what?
Hi.
Okay. So any signal with the bar on it,
That is low.
that is enable low, which means
Enable
that
low.
that line will be enabled whenever the signal on this line is low. So
Low. Yes.
IOM is the single line, and whenever this line is low, it is a memory operation. MUP understands it as memory operation. Whenever it's high, it understands it that IO operation. So since this is a memory read operation, uh,
That will be
opcode
low.
is in the memory, it will be low, right?
Low. Active low. Yeah.
So yes, until T2, right? And since ALE is low, reading signal read bar has gone low, which means this AD7 to AD0 will now read the data. Data here is what?
45H?
Y-
No, no.
No.
Oh,
Yeah.
the data from 2000. That is 3.
Yes. Yes. You
The
need
code.
different.
Yeah.
Yes. Just uh, when I say data for a fetch
Hmm.
opcode cycle, the data
Hmm.
that has to be
The code
fetched is
actually.
actually, yes, the opcode.
Opcode. Yeah, yeah.
Yes.
Hmm.
Okay. So during the fetch cycle, data is the opcode. So
Opcode. Yeah.
yes, this will get 3.
3. Yeah.
Yes. Uh, just a minute. Once I complete this, you can ask the question. So yeah. So 3 is loaded onto this bus. So actually, sir has thought that this goes, I mean, we don't need it after that because that is kind of true, but you can draw it up until here also because during this T4 cycle, this opcode is being, what do you say,
Decoded, I
decoded.
think. Yeah.
Yes, right. So either you draw it until here or up until T4 doesn't matter because there's no other operation that is being done on these lines, right? An opcode is there only, it has gone to the decoder and whatever. So yes, this is the and during this whole time we need to keep this data. So read will be here only. This whole is a memory read, and write will be, since no writing is done, it will be high during this whole
That
fetch
will be
cycle.
active high. Yeah, yeah.
Yes. Okay. Uh, yeah. So is the opcode fetch cycle understood?
Yes, it is clear now.
So up until this T4, by the time this T4 state is completed, MUPI has received the opcode, it has decoded the opcode, it has understood what has to be done next, or if something has to be done. Okay.
Just a minor point.
Yeah.
Here,
Yes.
the read bar signal can be
Uh-huh.
low for T2 and T3. That should be sufficient because, like, we are telling the memory to
Ah,
keep
yes,
data on
yes.
the data bus.
Huh. Since I drew it until here, so I just kept it there. But since there is no operation being done on read, it can go high here.
Yeah.
Like, yeah. Because the only thing that was to be done was to get the opcode and get it to the database. During this after this T3, the opcode is in the database going to the decoder, and during this T4, the opcode is being decoded. So yeah, it can go high.
Yeah. Thank you.
Someone else also had a question. Do you still have a question, or should I go on? All right. So yeah, by the time this T4 is completed, it has received the opcode, and it knows now that from the opcode, since it has received 3E and it has been decoded, that the instruction is MBI, and now it needs another data byte that has to be moved to the accumulator. That is what MBI means, right? So after this T4, this higher order address bus will again get the address of the next, the data that has to be retrieved. So that will be 2001. What will A15 to A8 get? Sorry, 2001. It will be the higher order bus get
20?
20. And for how much T states?
3?
The entire next
Mm.
entire machine cycle. So
Yeah.
20H will be loaded onto A15 to A8. What will happen to ALE?
ALE will be again high to read the
High.
code.
Yes.
No, sorry, to
Read the
enable
address.
this 80. Yeah.
Yes. So ALE will go again high for one T state so that the lower order address can be loaded onto this bus, which is
Yes.
here
0
01H.
1 0
Yes,
1 H. Yeah.
yeah.
Yeah. Yeah.
And ALE will go low
Low now.
after
Yeah.
this T state, so it will remain low. And after this, for the first like local T5 state, after this T5 state, the lower order address will be latched onto the latch, and it will be read signal will then after T5 will go low so as to read the data. And what is the data now?
It is 45H.
45H, right?
Mm.
And it will remain there. 45H. And since this data is being read, read will go low, remain low, and write will remain as it was. And since this whole instruction or the whole cycle was memory read cycle, this line will remain low, right?
Yeah.
This completes the whole what do you say, instruction cycle. This from
Yes.
T1 to T4 fetching is done. From T5 to T7, the data is being retrieved and it will be moved to A. Is it understood?
Yes, ma'am.
Okay. So, uh, okay. So this was example of memory read. What will happen in case of memory write? Let's see that. Since opcode fetches has to be there for all the signals, opcode fetch cycles will cycle for the T state signal conditions will remain same for all the instructions, right? So let's do an example of uh, memory, right? Yeah. So let's see. Move M, comma A, and the corresponding code for this is 77H. And what else? So let's draw clock first. Okay. Then we have going to AA, AD7 to AD0, ALE,
Ma'am, the
ABLE.
corresponding address of this code?
Oh, it can be anything. We're taking general example.
Okay.
Like whatever be the data, that will be moved to this memory location pointed by M. Okay. Arrow.
Yeah.
Mm. Okay, so this is our output fetch. Yes. So what will happen in, I think opcode fetch is clear enough.
Yeah.
Mm, okay. So what will happen in first T state? This A15 to A8 will get the address. Let's say it
Yes.
is at 2000 only. Okay. So A15 to A8 will get
20.
20H, right?
Yeah. Mm-hmm.
ALE signal will be high for first T state, then it will be going low.
Mm.
And because it's high for first T state, AD7 to AD0 will have
00H.
00H, right?
Yeah.
And after that, whatever is the read signal will be
77H.
uh yeah. Anyone has question?
Sorry, continue.
Okay. Then during this data read, this read signal will go low and write will remain as it is. Yes. And this is a memory read operation, so the signal will go low. So the corresponding code for MOV move is 77. So during the T4, T2, T3, T4, this line will have 77H. ALE signal is high during this time. ALE signal is low during this time. Read signal is low because the data is being read. Data here is during the fetch code cycle. Data is. Please remember this during fetch opcode cycle. Data being read is the opcode itself, not any other data. I mean, the name can be misleading. So that is yeah, so write is high, no writing is being done, and since the data is being the opcode is in memory, memory has to be read, so this IO memory line goes low. I think opcode fetch cycle is clear.
Yeah, ma'am.
Yes. So what will happen in the next cycle? Now the instruction MUPI has gotten the opcode. It knows that it has to write it in the memory, write some data in the memory, data that is in accumulator. Okay.
Yeah. Yeah.
So so it will know what address to go to,
Yes.
right? And what is that address? The address pointed by
Address of
M.
memory pointer.
Yes, address. So higher, how do I write it? Higher byte of address of M. Uh, I hope you understand, right? This is
Yes.
M. So this will contain higher byte of address of M, and during this first T cycle, this will first as in this machine cycles first. During T5, this will have the lower order
Lower order. Yeah.
of
Address
M.
of M. Hmm.
Yes, I am at lack of. oh. So yeah, and since it has to 87 to 80 have to have all the lines
High
have to read
ALE.
the ALE will be high,
ALE high. Yeah. Then
then it
low
will go
for.
low.
Hmm.
And now is the change. Since
It is write
and
operation, not read.
it is,
So
yes,
read
read will have to go
high
high and
for
it
the
will
whole
not go
cycle.
low.
Yeah.
Yes.
Yeah.
And
And
since
write will be low now.
after it
First T
gets
state.
the data, yes, right?
Hmm.
So the MUPI will get the data onto it,
Yeah.
which is content of A, and
Hmm.
write will go low when it has gotten the data from A, the content of A, and during these cycles 6 and 7, it will
High.
write
Hmm.
to address
Memory
location.
address. Yeah.
Yes. Okay. And since
Hmm.
didn't involve any IO, everything is being done on memory, this
Memory.
line will remain low.
Low. Hmm.
Right?
Now it's understood. Yeah.
Understood?
Yeah. 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 Yeah.
Okay. Anyone else? Do you have any questions regarding timing diagram?
Ma'am, here higher byte of address is stored in H register, and lower order byte of an address is stored in L register, right, ma'am?
Yes. Yes,
So
yes.
with
You
respect
could,
to that, yeah, sorry.
you could have written, I mean, I could have written this content of H here and
Yes,
content of L here.
yes. Okay, ma'am. Thank you.
Anyone else? Hmm. Okay, so I think timing diagram is fine. Uh, okay. Any case you don't understand, you can ask in the course forum. So next thing is program status word PSW, which is a register pair of A and flag register. Basically, it contains all the current status of MUPI. Like, uh, all the after all the operations are done, the result goes to accumulator, right? And after some operation is being done, flags are
Changing.
modified, right?
Yeah.
So after every cycle, accumulator will get new data, flag register will get new data depending on what the operation was, right? So together they contain the current information or current status of the uh, MUPI. So together they make up this word is 16 bit array. So yeah, together they're called program status words. So whenever you have to, or in the program, it is necessary to execute some subroutine or call some other thing, and you want to retain all the you want to save the status of your current main program. What do? You save the or you push the this program status word, the 16 bits to the stack, and you after you uh, what do? You execute your subroutine or whatever is to be done for the meantime, and after your subroutine is being done, after you get whatever your results were, whatever you were desiring to get, or whatever operation you wanted to do, you pop back the program status word, that is 8 byte and 8 byte, from two address locations of the stack, and you can resume from wherever you left off before the subroutine was called. Okay, so yeah, that is program status word. Stack, I think we discussed last time also. It acts as last in, first out, and what else? It can be used to store the current status of the MUPI, or it can be used to store data. It can be used to what else? Yeah, that's it. So yeah, it is used to store obviously the return address also. Once you call subroutine, you have to return to the address. So the program contents are also stored in stack so that you can return to the main program right in the right place, right? So that is stack. Next is subroutines. So subroutines are like these mini programs only. Can you see my screen? I think it's visible.
Yeah, visible.
So subroutines are like the small mini programs that you want to execute while not leaving the actual main program that is being executed. So for the subroutines, you have to initialize. These are the main things that you do for the subroutines. For executing subroutines, you initialize the stack pointer, because once if you're calling a subroutine with and in the main program, say you are at this address, right? Program counter, if program counter is pointing at this address, and here you have to call some subroutine which is stored at some other address, and you After subroutine, it is like understood that you want to get back to this address only. So what do? You initialize, first of all, you need to initialize the stack pointer so you can store this address to the stack. Like you have to initialize stack pointer, or the address will be stored at some rubbish, or some place where you won't know where to get it back from, right? So initialize the stack pointer with some known value of address location, and you push the address of this location, the main program. This is the main program. This is your subroutine. You push the address into the stack. This is the stack, right? So once you initialize the stack pointer, stack pointer will point to some location, and there you'll store the address of this instruction. You'll store it. You'll go to the subroutine, perform all the instructions that are there in subroutine. You return from there. And how do you return from there? After popping out the address that was pushed earlier before calling the subroutine. You'll get back the address from stack, and that's how you get back to the main program. And for the time being, or if it is required that you store the current status of the MUPI also, then you push this program status word also. And once you get back to, it has to be in sequence. So once you get the address back from where to get resume in the main program, you pop out the PSW also, so that you can resume exactly where you were. Like you get the contents of the accumulator, contents of the flag register, and yeah, that's how subroutines work. Is there any confusion regarding this, or should I move on? Understood?
Yeah.
So, do I want to say anything else? Okay, yeah. So moving on to the interrupts. So interrupts are like, say your MUPI is executing some main program, and there needs to then the urgent need has occurred that you have to go to some you have to perform some other instruction routine that in between this main program. So, and this instruction routine is, as we call it, ISR. And so interrupt is basically calling an instruction which executes this ISR, right? So yeah, basically that's the interrupt. Since MUPI cannot always keep checking that, okay, do I do this? Do I do this? Or should I keep checking this flag or this register? Instead of that, MUPI calls in for the interrupts. There's a provision to call interrupts, hardware, software, however, so that it can perform desirable result whenever the need occurs, right? So that is the function of interrupt. So classification interrupts can be maskable, non-maskable. Like there can be some routine that can wait. They are not at priority. So you can mask those interrupts. And some interrupts can be of highest priority, that whatever the main program is doing, it has to leave that and do this instruction first. So those are non-maskable interrupts. Then like I said, there is some ISR that has to be performed when interrupt is occurred. So, where is this ISR? Like, if the interrupt has occurred here, then MUPI has to do some other thing, but here is the main program, right? So, after the when the interrupt occurs, this MUPI might get the address of uh, where to go to look for or execute the ISR instructions, or it might not, depending on the kind of interrupt, right? So there are different kinds of interrupts, software interrupts or hardware interrupts. So basic software interrupts are not mostly used. We'll use hardware interrupts only for the majority of the cases. It's not like they're not used; they are very rarely used. So yeah. So depending on the type of interrupt, whether it has some fixed address to where to go to perform the instruction if that interrupt is occurred, we call them vectored or non-vectored interrupts. So if an interrupt has fixed address to which it will go to, then it is called a vectored interrupt. And if it does not have the fixed address, it's called the non-vectored interrupt. Right? That's the basic definition. Then there's yeah. So interrupt vector is just the address of the ISR to which the MUPI will jump to if the interrupt occurs. And interrupt vector table is just like list of addresses or the location specified for any interrupt. Let's say, for example, for
Ma'am,
RST 5.5. Yes.
ma'am, if you don't mind, can you explain a vector and non-vector interrupt again, please?
Yeah. Okay. So if um, let's say here's the main program, right? And if during this program some interrupt occurs, and let's say that interrupt is uh, you know the names, right? Trap, RST, 7.5, 6.5, 5.5, then INTR. These are the five hardware interrupts. So let's say this interrupt, which one? Yeah, 5.5 occurs here. So for since uh, okay, I'll out of these five, all the trap, RST 7.5, 6.5, 5.5 are vectored interrupts, and INTR is the non-vectored interrupt, which means if any of these four vectored interrupts occurs, MUPI knows the exact location or address location where it has to go to perform the ISR of that interrupt.
Okay, ma'am.
Okay. So
Okay.
if this RST 5.5 occurs, MUPI will know. Okay, so these names are also logical. Okay. They are not named SAK 5.5. Just program. The designer wanted to name them as just some random number. 5.5 is named so because for RST 5.5 because its ISR is placed at uh, 5.5 into 8. If you do this multiplication, you'll get the address of the first instruction of ISR of this interrupt. So, can you do this multiplication? 5.5 is what? 40, 44. So, you get 44H. So, if this interrupt occurs, MUPI will know that it has to go to this 44H. Let's say this is location 44H. MUPI will go to 44H where the ISR of this interrupt is placed.
Okay, ma'am.
Okay.
Ma'am, may
Yeah.
I interrupt?
Yeah.
Is it 44H or 44 decimal?
It's 44H.
It's
44H.
it's
All the numbers that you see because MUPI doesn't work in decimal, it works in hexadecimal, right?
Yeah.
So
But
it has to
in
go
case of
to
RST2, say it is RST2, so 2 into 8, that is 16 base 10. So
ah,
that
okay.
RST jumps to 10H location.
So
That
let me.
equivalent, yeah.
RST2 is the software interrupt. I'm talking
Ah,
about right now this hardware interrupt.
hardware. Okay, okay.
Right?
Mm.
Yeah. Someone was asking question. I'm not able to see.
Then RST 5.5 should be 5.5 into 8 should be like 2C H no ma'am in hex. 44 means it
No,
is in decimal.
see, the interrupt vector table gives you the addresses from the all the routines. So this is from 000H to 00FFH. So I also explained this in class that all the ISRs are between these addresses only. And if you see 00H, like these numbers are hex numbers. They're not decimal
Yes ma'am.
numbers.
No, ma'am, I think there is a confusion. This multiplication is in decimal and we have to, I think, convert it into hex.
Yes ma'am.
Yeah, I think
Oh,
this
I
is
get.
also.
Okay. Yes, I get it. Right. I'm sorry. Yeah. So this is in decimal. Yeah, my bad. This is in decimal and 44 when converted to I'm sorry for that.
Hex.
44 when
Yeah,
converted to
yeah.
hexes is
Yeah,
actually what is it?
yeah, that's
32
I'm trying to
plus.
do.
Yeah. Yeah, got it. So yeah, 44 is what? 32 plus 12, which is 16 twos are 2C. Yes, it will go to 2C. Sorry. Yeah. So this multiplication gives you in decimal and this will jump to 2C. Yes, you were correct. So this is the case for RST 5.5 and similar for you can calculate it for 6.5, 7.5, and then there can be cases when if you see the difference between these are uh, 8 locations. So there can be interrupts where you cannot put in ISR in 8 locations. So what do you do? What a programmer does, it'll since MUPI has to go to this location that is specified here. So in this ISR routine locations, it will point out to some other location where some other where actual ISR is placed if it's longer than the location spaces given here. So there it will perform. It's like a subroutine only. It will come back here. Here it will get address back of where the main program was left off. And yeah, the MUP can resume its normal main program instructions. Right?
Just an addition. From the ISR, it won't go back to this 2C location, right? Already we have only 4 bytes left.
I mean, yes, the return, whatever the return path is.
Yeah,
I
so
just
in
wanted
that.
to say it quickly. Yeah.
Okay.
Which is running out of time. All right. Uh, is this clear?
Yes ma'am. Non-vector interrupt how it behaves ma'am. Like
So this one was for vectored. In non-vectored, addresses provided by the hardware itself, since these are hardware interrupts only. In non-vectored, whatever hardware or whatever peripheral device is causing that interrupt, it will provide the address of the ISR. So only INTR is non-vectored, and whatever hardware or peripheral device makes that interrupt to occur will provide the MUPI the address of its ISR, wherever the ISR is placed.
okay,
That's the
okay
only
ma'am. So
difference.
whenever the interrupt occurs in non-vector scenario, whenever the interrupt occurs, the MUP will acknowledge, and then after that the hardware will send the corresponding address to microprocessor.
Yes, during the interrupt only that the address of the ISR is sent. And since this INTR, so priority, I think it was discussed, I don't remember. So these are the 5 uh, interrupts: trap, RST 7.5, RST 6.5, and INTR. So there can be cases where there are multiple interrupts, right? Like MUP can have multiple peripheral devices connected to it, and many of them can not getting the word, can cause the interrupt to occur, right? So if there are simultaneous interrupts, which interrupt should the MUP entertain first? So for that, there is a priority order from okay, so this has got the highest priority, then second highest, third highest, fourth, and fifth. So this INTR is the lowest priority interrupt. Trap is the highest priority interrupt. Okay. So if there are multiple devices causing multiple simultaneous interrupts, MUP will entertain the interrupts according to this priority order. Okay.
Okay.
So these are non-vectored. I think I have covered everything. Mm. Yeah, so let's move on to the problems. Yes, okay. So, like last time only, we don't have many calculations to be done, so you all can work together and answer in the chat box, right? So, yeah. So if n denotes the number of clock cycle and t denotes the clock period, huh. So what is the duration of execution of loop once execution of loop, or the just say the time, what will be the time taken by the instructions?
N into T. See.
And everybody agrees,
Yes, ma'am.
right? N into T. Yeah. All right. So is the contents of the what will be the contents of accumulator after execution of the following instructions, right? So first instruction is MVI A B7H. You can see the screen, right?
Yes, ma'am. Now it's visible.
Yeah. So yeah. After this, what is the instruction first? What will this do?
It will add both the datas and then RAL.
Yeah, step by step. Okay. So what will MVI A B7 comma B7H do? A will get B7, which means let's not draw this. B7 is what in binary? D is 11, which is 1 0 1 1. 7 is 0 1 1 1. Or A will do what? or the A will with itself, which means the content of A will be same 10110111, and RAL will do what?
Left shift of accumulator,
Mm-hmm.
content of accumulator, and it will exchange that bit with carry.
Yes. So for this, we need to know what will be the status of carry.
Content of carry, yeah, yeah.
Yes. So this OR instruction modifies the carry flags. Sorry, flag registers. So carry flag will be what?
Set.
No additional, nothing has been done. 0, right? No such operation was done that had to modify carry flag,
Okay.
right? Since nothing was changing the carry flag, it will be 0. And RAL will do what? Shift all the bits to the right with the carry, right? So what will we get?
Madam, sorry to interrupt.
Yeah.
ORing operation will never set carry, right? Carry will be never set.
Yeah, that's what I said, that no such operation was done that had to modify the carry, right?
Okay.
Sorry, I'm not able to hear you clearly.
Sorry, when we do OR operation, carry flag will be cleared. Uh, no operation will be done to set that carry. It's always cleared.
Yes, yes. Yeah. So, yeah, so we know after this instruction carry flag is 0, carry bit is 0. What will be the contents of accumulator after this RAL then? Everything will be shifted to left. 0 1 1 0 1 1 1 0, which gives us 0110 is 6,
6 6
1110 is
6E.
E.
14E, right? So answer is 6EH, right? Any confusion regarding this?
Just to add clarity, I'm not sure whether I conveyed correctly. So even if
Mm-hmm.
we have this move immediate A comma FF instead of B7,
Mm-hmm.
the question had it been FF, even in that case, FF
Mm-hmm.
ORing with FF will give me again FF. Like carry flag will never get set in OR operation. That's what I wanted to convey.
Yeah, even I wanted to convey that only. I think,
Thank you, ma'am.
yeah, okay. So, yeah, moving on to the next question. Yeah, so we need to match the addressing modes with the given instructions. Can you do that? What is this LDA30FF? What kind of addressing mode is this?
It is direct addressing mode.
Think again.
Direct.
Really?
Yes, ma'am.
I
Yes,
think
it's
C
direct.
is the answer. C.
Let me see. Yes, yes, direct addressing. C is the answer. So this is direct addressing. Move A comma B is
Implicit.
implicit. LXI H comma 2050 is
Immediate.
immediate, and
Madam,
RLC
is it not
R-
register?
excuse me,
Move A comma B, is it not register? Both the operands are registered like A and B. We are
yeah,
yeah, that is register addressing mode. It will
yeah.
be.
Okay, so this is direct addressing. Move A
Yeah.
comma B is
Register addressing.
register addressing.
Hmm.
LXI H is
Immediate and
immediate.
RRC implicit.
Yes. So which gives us C as correct answer, right? Okay. Next question. Are you able to see the screen?
Yeah, it's visible.
Okay. So how many times will the following loop be executed? So there's an instruction XRA then MVIC comma 05H.
5 times.
Anybody else? Is anyone working? All right. This XRA has nothing to do with the loop. In this instruction, we are loading 05 to C, and then we are decrementing C, and then there is this conditional jump to loop, which means this decrement C will be executed uh, as many times
The
this
value of C.
value of C that was loaded at the starting of the or before the loop, right? So this will continue until C becomes 0, and since C is 5, it will take 5 iterations to make it to 0, right?
Yeah.
So loop will be executed 5 times. Okay, next. So if a microprocessor uses 5 megahertz clock, what is the duration of one T state? I mean, one T state can be calculated as 1 by the frequency of mu p.
0.2 microseconds.
Frequency is 5 megahertz. And this gives us zero point 0.2 microseconds, right? 0.2 microsecond is the correct answer. Next question. So, what is the status of zero flag and the contents of accumulator after the execution of following code? And assume that contents of all other registers and memory locations are unknown. Okay. What will we need to see what is the status of zero flag and the content of accumulator. So, what will be the content of accumulator after this instruction?
85H.
Yes. So, A will be 65H.
Yeah.
Right. Then you are moving 32 to B register. B will get 32H.
32H.
This compare B, what will this do?
It will compare the content of B with the content of A.
How?
Sorry.
How will it compare the contents?
Uh, if A is greater than B,
That's
then
that's the end result. But how will it know that A is greater than B or less than B or equal to B?
Subtraction, ma'am. Subtract A from B.
Yes. So
65
compare
minus
B does
32.
what? Yes. Compare B does A minus B, which means 65 minus 32 and this will be 33H, right? So
Yeah.
now once the result is known, it will see that this is positive or negative, and from that positive or negative, it will decide, the MUP will decide whether A is greater, B is greater, or are they equal. So if it is positive, negative, this will be decided after this operation is being done, this subtraction is being done. So since this is a positive, negative, or zero, three outcomes are there, it will obviously affect the flags. So since the answer here is positive, what will be the status of zero flag bit?
0. It will be 0.
0.
Zero, right?
Yeah.
Positive, zero. So what is the answer now? The zero flag bit is zero, and the
Option C.
accumulator is
C option. Yeah.
so after subtraction, the result will go to A only, so A will be overwritten and it will contain 33 now. So this is the correct answer, right? Any confusion regarding this?
Sorry, ma'am. Compare operation won't change the value of the registers. It will just affect the flags.
Really?
Then I need to check.
I think it no, it doesn't. Yeah, it doesn't.
Remains unchanged.
Yes, yes, it remains unchanged. Since it's not actual subtraction instruction, it won't change the contents of the accumulator. It only compares and then modifies the flag bits. So yeah, A will contain its original value 65. So A is the correct answer. Right? Okay. Next question. Yeah. So how many bytes does the following set of instructions occupy?
5
So
bytes. C.
yeah, let's calculate it one by one. So MVI MVI A comma 35H is how many byte instruction?
2 byte.
2 bytes.
2 bytes. One for the opcode and one for this 35. MVI B
Yeah.
comma 2 again 2
2.
byte.
Yeah.
And
And
since
add
this
B 1
ADB
byte.
doesn't require other data byte, it is 1 byte. So total becomes 5 bytes.
5 bytes.
Is the correct. Okay. Next question. So, for the 8085 program given below, content of the accumulator after execution of the program is what? Okay, so let's see. So these are the addresses, right? So what will this instruction do? A will become 45 after this instruction, right? Then move B comma A will do what?
Copy the data of accumulator into B. That is, B will be 45H.
Yes. So B will get the data of A, which is actually 45, right? Now on 3003, there is STC, which means set carry. So this instruction doesn't do anything to our data. It just sets the carry.
Yeah.
Carry
I think
flag becomes 1.
answer B will be the right, I think. Yeah.
Yeah, can we work step by step?
Mm.
Sorry to, yeah, everybody else needs to understand also, right? So yeah, CMC will do what? Complement the carry. Okay, this let's the carry bit. This one complements the CY. This carry becomes the complement of itself, which is 0. Complements carry, right? What will RAR do? Shift the contents of,
Right, rotate the contents of accumulator and it will change with carry. Exchange
yes,
with
it will,
carry.
yes. So after changing, after moving to the right, it becomes, I think it becomes, yeah, 22H. A will become 22H. And then this next, I think this is clear, right? I didn't do this completely.
Yeah, clear.
Yeah. So this XRAB means XOR the contents of B with the contents of accumulator. So after XORing, and what is the content of B? B right now is 45,
45H. Yeah.
A is 22. So after the XOR operation, we get 67H. Okay. You can try doing this like bit by bit. You'll get 67. Since we are running out of time, I don't want to spend time on this. Okay. Should I do this or is it fine?
No, it is 67. Yeah, 67H.
Right?
Yeah.
So C is the correct answer. I've just told you this is XOR A XOR B. Okay, so next question. In 8085, which mode of addressing does the CMPM use?
Is it direct addressing mode?
No, it can't be. M is used here.
Uh-uh. Mm.
Direct direct addressing is for when address is given. Here
Mm.
M, the address pointer is given, which means address is being given in the instruction, but it is pointed by some
Then
register, right?
in indirect addressing mode it is.
Indirect addressing. The address is being given in the instruction,
Given
but it
the
is being
pointer. Yeah.
through the pointer, so it's indirect addressing, right?
Okay.
I should have written it so CMP M. Address is being pointed by M, so it is indirect addressing, right? So next question. Between DCR and DCX instructions, the flag statuses are affected by which of the following? Either of them, both of them, neither of them,
Only DCR, ma'am.
only DCR. Does everyone agree?
Yes.
And why so? This is the correct answer, but why is it not affected by DCX?
DCX is done using a register pair decrement is done.
Okay.
DCR is only done by a single register, so
Yes.
it will
Yeah.
affect.
Hmm. So
Can,
DCR is done for the 8-bit accumulator, right? But this DCX is implemented using incrementer decrementer register pair, and the incrementer decrementer doesn't affect the flags. That is why that is why it doesn't affect the flags. DCR is done using 8-bit accumulator. Whatever the operation is being done, accumulator is involved, and so the flags are modified. Since DCX is not implemented like that, it doesn't affect the flags. Okay, alright. Next is after execution of the given statement, determine the status of flag register content. Yeah. So what will MVI A do? Okay, the bits are written a bit. So this hash doesn't mean anything. This is just a number, and 0 also doesn't mean anything. So A will get BFH data, right? ADI A comma IB means yes. So ADI A means A will get A plus 1B H, which means this addition has to take place. So what will be BF? BF is 10 BF 1011 and 1B is 0001 1011. After adding, what will we get? Is anyone doing? 1 plus
Yeah,
1 is
trying to.
0. Yeah. So this is 3, 1, 0, 1, 1, 1.
It is.
Yeah. So this is what I'm getting. Yeah. So this is the, and remember we need to get the status of register, not the actual addition, right? So the answer is this, but what all bits do get modified in flag register? First of all, we need to see carry flag. Is there any carry here?
No.
No,
No.
no,
So
ma'am.
carry flag will be
Carry will
0.
be 0. Yeah.
There is an auxiliary carry. Is there an auxiliary carry here?
Yes.
Yes, ma'am.
Auxiliary carry is when you get from this lower byte, carry from this lower
G3.
byte to
Yeah.
the, yeah.
Yeah.
So
Auxiliary
there is
carry
an
is 1.
auxiliary carry is 1.
Yeah.
Then there is a parity flag. Parity is 1 for even number of ones in your answer and 0 for odd number of ones. So here the number of ones in the answer is 1, 2, 3,
Even
4, 5. 5 odd,
5. 5. Sorry. 5.
right? Odd number of ones.
Odd
So
number. So it will be 0.
0. And so your flag will be what? Mhm. Okay. I have not written. Only auxiliary carry is 1. Everything else is 0. So auxiliary carry is this one. So this will be your answer. Do we have this in options? Yeah, I think C. Yeah.
C option.
Yeah. So is this example clear? Anyone? All right. Moving on
Yes,
to the
correct.
next question. The clock frequency of 8085 is 5 megahertz. If time required to execute an instruction is 1.4
Ma'am, please
microsecond,
change
then
the
what is
slide. Yeah. Now it is.
yeah, that's changed, right? Huh. So what will be the number of T states for executing this instruction? How can you do this? So yeah, the clock frequency is 5 megahertz and total time taken to execute this instruction is 1.4 microseconds. And we need to calculate the number of t states that it required to execute the instruction, which means just simply the way you calculated the total time before, it will be one. So, uh,
7.
yes, so total time is actually number of t states divided by clock. And to calculate t states, you get time into total time into the clock frequency, which is 1.4 10 power minus 6 into 5 into 10 to power 6, which is 1.4 into. Did something wrong here, right? Oh, oh, yeah. Just wait. Yeah, so we need to calculate the time taken to execute, or time taken in one t state. Time taken for one t state will be one time for one t state will be 1 by the clock frequency,
Yeah,
right? That will be 1 by 5
5 megahertz.
into 10 power 6, which is zero point 0.2 microseconds, right? So total number of
Ma'am,
t states
ma'am,
will
it will
be
be point 2 now.
yeah, sorry. I shouldn't be in hurry. So number of t states will be this total time divided by the time taken by single t state. That will be 1.4 microsecond by zero point 0.2 microsecond, that is 7, right? So the answer is C. So the instruction took 7 t states to complete the execution, and the actual time was 1.4 microseconds. Okay, into the next. It's clear, right? How we calculated the. Okay, no questions. Yeah, so what are the states of auxiliary carry and carry flag after executing this program? Let's see. So what will this instruction do? MVI H5D, H comma 5D. It will load H will this, right? 5D. Then next is MVI L6BH, which means L will get 6B. Then this is move A comma H. A will get the contents of H. A will get the contents of H, which is 5D. And then add L, which means A will get the contents of A plus L, which is 5D plus 6B. Now, if you add this, what is 5D? 5D is 0101, right? D is 1101, and 6B is 0110, and D is 1011. After adding these, we'll get 0, 0. So, one here, one here, one carry, one 0, 0. Yeah, so this is the answer. Has everyone worked this out?
Yes, ma'am. Same
Same
answer.
answer? Okay. So what are the statuses of carry flag and auxiliary carry?
Auxiliary carry will be 1 and carry
Yes.
0.
Yes. Since we didn't get carry from this operation, carry flag
Yeah,
is 0, and we
carry is
got
0. AC is 1.
carry from, yeah, from
C, option C.
AC is 1. Option C is correct. Yes. Everyone clear? Please ask me if anything is not clear, okay? Or else I'll keep going like this. Yeah. Can you see the screen here? Contents of stack pointer after executing the following instructions will be. So first of all, the stack pointer is initialized. Uh, LXI SP comma 3FF means the stack pointer will get this address, right? So, and we need to remember that stack will point to the top of the stack, which means if this is the top of stack and 3F, F, F, and it fills in as LIFO, last in, first out, right? So anything that is now pushed into the stack will come to the address above this one, 3FFF, right? So yeah, stack pointer has the value
A, option
3FFF.
A, I think. After push B.
So what does push B means?
Push B means to keep the contents of register B and C, means BC pair into stack.
Yes, correct. So push B will push the content of
Register B and C.
register BC pair,
Register.
and which means there are two bytes that need to be pushed, B and C.
Yeah.
B will be pushed here, C will be pushed here. So stack pointer will point to the top of the stack now, which means address of this will be 400. No,
No, it will be
three,
automatically
three. Yes,
decremented by 1
yes, decrement.
and then
Yeah.
then it will
So this will be 3FFE, and
yeah
this will be
contain B. Yeah. 3FFD.
3FD, right?
Yeah.
So now
Yeah,
since
yeah.
this is the top of stack, stack pointer will point to this address.
Yeah. A.
Is the correct answer. I hope it's clear to everyone, right? Okay, let's move to the last question. So, if 8085 has two instructions for dealing, what are the two instructions that it uses to deal with subroutines?
Call and return.
Call and return.
Calling it, right? Call to call the subroutine and return to get it back to the main program. Yeah, I think that is clear. Yeah, do you have a question? All right. Mm-hmm. Yes, I think, yeah, that's it. Uh, yeah, so I just wanted to discuss this last thing. So while doing the loops or while loading the registers with the numbers that you want to iterate for given instruction, the number of times you want to perform an instruction, you load a register and then you keep decrementing that register, right? So there's this just one interesting example that let's say this is the program MVISP comma any number. Let's say you loaded with some number which I'm calling count right now, and then you keep decrementing it and you jump to 0 if it's not 0, and loop goes in here, right? So, you know that the loop will be executed the number of times this register is being loaded, right? So if I load, let's say 01H, how many times the loop will be executed?
One time.
One time. What if I load it with FF?
255 times, ma'am.
255 times. This means one time. 255 times. What if I load it with 00?
It will not be execute.
It will be executed. I mean, let's say, take this example, if I load it with 00H, right?
Mm.
And the next instruction is to decrement C. Now,
Okay,
if you
it will go to FF.
will go to FF, right? Correct. You just had to think a little before
Yeah.
answering, right?
Yeah, yeah.
So,
And it will execute 255 times.
no. See, yeah,
255 plus 1.
plus
256
one.
times.
So, for first time, this will go to this next instruction, which will make this FF, right?
Mm. Mm.
So for this first time for which the 0 becomes FF, the
FF.
loop has already been executed once, right? And
Mm.
after
Mm.
it goes back to this, it is now C is now FF, and similar to this case, now it will execute 255 times
255
until
times,
it
yeah.
becomes 0 again,
Mm.
right? Because
Mm.
jump if not 0 is here, not here.
Mm.
You need not to jump to conclusions before stepwise logically executing the instructions.
Yeah.
So yeah, go instruction by instruction. This will help you in programming questions. So I don't know, I thought it was interesting, so I wanted to discuss. Yeah, that's it. Yeah, thanks for joining, and thanks for your patience for that little hiccup at the start. Yeah, any questions will be entertained in the regarding this lecture also, this tutorial. Yeah. See you next week. Good night.
Good night, ma'am. Thank you.
Bye.